Okay, let's jump right into this explainer. If you've ever stared at a machine learning glossary and just felt completely overwhelmed by the sheer volume of decision forest terms, well, you are definitely not alone. Today, we're going to cut right through all that noise. We're taking the key terms, definitions, and metrics surrounding decision forests and organizing them into a structured journey so you can see exactly how these incredibly powerful algorithms actually think.
But, before we even hit the roadmap, I actually want you to picture a classic game guessing the number of jelly beans in a giant glass jar. How would you do it? I mean, would you try to calculate the volume? Would you just take a completely wild guess? Keep that in the back of your mind, because the answer to how we solve this jelly bean problem is, surprisingly, the exact same secret to how some of the most advanced algorithmic models function.
Okay, here's our roadmap to make sense of this massive glossary. 1. Anatomy of a decision tree. 2. Making choices with conditions. 3. The math behind the split. 4. Growing the decision forest. And finally, 5. The wisdom of the crowd.
Let's kick things off with Section 1, Anatomy of a Decision Tree. The foundational building block of this entire system is the decision tree itself. Simply put, it's a supervised learning model that organizes a series of tests and outcomes in a very strict hierarchy. It's literally the basic unit of logic that everything else we talk about today is going to rely on. Now, what's really interesting here is how developers borrowed botanical terms but turned them completely upside down. So in a decision tree, the root is actually the starting point at the very top. From there, the data flows downward through nodes, which are just the points where tests happen, and it ultimately ends up in the leaves. A leaf doesn't test anything, it simply spits out the final prediction.
And this brilliantly illustrates what we call the inference path. When the model is actually making a prediction, it takes a specific example. Let's say, an example where mathematical features are defined as x equals 7, y equals 12, and z equals -3. It steps that data right through the tree, starts at the root, travels through the necessary conditions, and terminates at a specific outcome. In this case, those exact features lead us straight to leaf zeta.
Moving on to Section 2, Making Choices with Conditions. Having mapped the basic anatomy, we really need to understand how the tree directs traffic and makes its choices at each of those junction points. And that brings us to the condition. A condition, which, by the way, you'll also hear referred to as a split or a test, is the exact moment the algorithm asks a question to divide the data. It's basically the gatekeeper of the node. Now, trees can ask these questions in a couple of different ways. An axis-aligned condition is incredibly straightforward. It focuses on a single feature, comparing it against a threshold, like simply asking, is the area strictly greater than 75? But as we know, the real world is often more complex, and that requires an oblique condition. This involves testing multiple features together, like evaluating if height plus width is greater than 12. For categorical data, things get even more specific, with an inset condition. This is super efficient. Instead of running complex mathematical threshold tests, it just checks if a feature belongs to a specific list. For example, asking if a house style is Tudor, Colonial, or Cape. It's just a quick yes or no to a predefined group.
Let's dive into Section 3, the math behind the split.
So the crucial point here is figuring out exactly how a tree decides which condition is the best one to use in the first place. Enter the splitter. During training, the splitter is the routine responsible for finding that perfect condition, and it relies on two crucial metrics. First is entropy, a concept from information theory that measures just how unpredictable a distribution is. The second is Gini Impurity, which calculates the sheer probability of misclassifying a brand new piece of data.
Let's look at entropy in action, often called Shannon's entropy. If we have a dataset split with 100 examples of value 1 and 300 examples of value 0, so a 25-75 split, and we plug that into the entropy formula, it yields an unpredictability of 0.81 bits per example. To put that into perspective, if the set were perfectly balanced at 50-50, the entropy would be exactly 1.0. The closer to 0 you get, the more uniform and predictable the data actually is.
But we don't just calculate entropy for the fun of it, right? We use it to find information gain. By calculating the entropy of a parent node and then subtracting the weighted sum of the entropy of its child nodes, we can see exactly how much uncertainty we just eliminated. In this example, 0.6 minus 0.14 gives the tree an information gain of 0.46. The splitter's goal is always to maximize this gain. Find the question that organizes the chaos best. All right, section 4, growing the decision forest.
Okay, let's zoom out from the mathematical weeds of a single split and see what happens when we scale this whole thing up. The reality of machine learning is that a single decision tree, while neat, often just isn't powerful or accurate enough on its own. So we create a decision forest. This is a model that aggregates the predictions of many trees into one robust answer. But to make this work, the trees have to be diverse. They can't all just memorize the exact same data.
To build that diversity, developers sample the training data. And here is a fantastic little piece of trivia from the glossary. Sampling with replacement often confuses English speakers because it sounds like substitution. But actually, it comes from the French word remplacement, meaning putting something back. So if you pick an item, like a fig, from your data pool, you put it back, meaning it can be picked multiple times.
This totally unique sampling technique is the beating heart of a concept called bagging, which is short for bootstrap aggregating. By training each model on a random subset of examples sampled with replacement, you are intentionally injecting random noise into the models. It's the core of a random forest, ensuring no two decision trees look exactly alike. This makes the whole forest so much more resilient to new data. And to make the forest even smarter, developers use a few other powerful tactics. First, there's attribute sampling, where nodes only get to look at a random subset of features. Next is out-of-bag evaluation. This is a really clever way of rapidly testing a tree using the data that was left behind during bagging, which saves massive amounts of computational time. Then there's gradient boosting, where weak trees are trained iteratively to fix the errors of the trees that came before them. And finally, shrinkage, a parameter that controls the learning rate and stops the model from overfitting. At the end of the whole shebang, how do we actually know what the forest cared about? Well, that is where variable importances come in. These are scores generated after the fact that tell the machine learning experts which features actually drove the model's decisions. It reveals, for example, that when predicting a home's price, the house's size was mathematically far more critical than its age. And finally, section 5, the wisdom of the crowd. This incredible aggregation of data, testing, and mathematical consensus brings us right back to our opening question and to the fundamental philosophy powering these systems. Remember the jelly bean jar? This concept is called the wisdom of the crowd. If you ask hundreds of people to guess the jelly beans, most individual guesses are going to be wildly inaccurate. But empirically, the average of all those flawed human guesses perfectly pinpoints the actual number. Decision forests, these ensembles, are literally the software equivalent of this exact phenomenon. They aggregate individually weak, flawed decision trees into surprisingly brilliant predictions. And that leaves us with a pretty provocative thought to take away. We've seen how meticulously these models use entropy, conditions, and bagging to aggregate data. If an algorithmic forest is undeniably smarter, faster, and more accurate than a single tree, is a well-trained algorithmic consensus ultimately more trustworthy than our own individual human intuition? It's definitely something to chew on next time you see a machine learning prediction. Thanks so much for joining me for this explainer, and I'll catch you in the next one.